Welcome to Generative AI and Agentic AI, Concepts, Frameworks, and Multi-Agent Software Engineering. In this lecture, we'll explore how generative AI, the technology behind models like GPT, differs from agentic AI, where systems can act autonomously. We'll start with definitions and the foundation of it all, large language models and the transformer architecture they're built on. Then we'll discuss prompt engineering, effectively programming these models with language, and move into how to structure AI agents. We'll cover different agent architectures, from simple reactive agents to more advanced planning ones that use tools and even reflect on their answers. We'll expand to multi-agent systems, situations where multiple AI agents communicate and collaborate, including concepts like the BDI model of agency and how agents exchange messages. The lecture introduces popular frameworks and libraries you can use to build these systems, such as LangChain, AutoGen, crewAI, and more, and common design patterns that have emerged for orchestrating agent behavior, like having a planner agent with worker agents, using an LLM as a router, evaluator agents for self-correction, etc. We'll see how all this theory applies in practice for data science tasks. Imagine automating data pipelines or analysis using AI agents. Finally, we'll address crucial considerations around risk, governance, and safety. Autonomous agents are powerful, but we need to control them. And we'll look at some real-world case studies where companies have deployed these AI agent systems. By the end, you should have both a conceptual understanding and practical insight into multi-agent AI systems. Let's begin with generative AI. Generative AI refers to any AI system that can create original content in response to user input. This could mean writing a paragraph, composing music, drawing an image, or even generating source code. It's generative because it doesn't just analyze data, it produces something new. Under the hood, generative AI systems are driven by generative models. For instance, GPT-4 is a generative language model. DALL-E is a generative image model. These models are trained on massive data sets, and they learn the statistical patterns of that data. Then, when you give them a prompt or some initial input, they use those learned patterns to generate output that is often novel yet sensible. For example, if you prompt GPT-4 with, "Write a short story about a lonely robot," it will produce a unique story, not copied verbatim from its training data, but invented word by word following the style it learned. Likewise, an image model given "a castle on a cloud" creates a new image following the concept of castles and clouds it learned from training images. Generative AI has seen an explosion of impact. We have AI writing assistants, coding copilots that generate code, tools for synthetic data generation in data science, and creative applications galore. The key takeaway: generative AI is about content generation on demand, powered by large-scale models that learn from lots of examples. It's the foundation for what comes next, because many AI agents use generative AI, like an LLM, as their brain. You'll often hear the term foundation models in discussions of generative AI. A foundation model is essentially a very large-scale model trained on a very broad data set. For instance, all of Wikipedia and lots of web text for a language model. They're called foundation because they serve as a base that can be adapted to many different tasks. The classic example of a foundation model in language is GPT-3 or GPT-4. They weren't trained for one specific task like translation or sentiment. They were trained generally to model human language, and then they can be prompted or fine-tuned to do all sorts of things. Large language models, LLMs, are foundation models that deal with language. These are the GPTs, BERTs, llamas, etc. that you've heard about. Technically, most state-of-the-art LLMs use a neural network architecture called a transformer. Transformers revolutionized how we handle text by using a mechanism called self-attention, which lets the model weigh the relevance of different words in context. So it can, for example, figure out that in the sentence, "the animal didn't cross the road because it was too tired," that "it" refers to the animal, not the road, by attending to context clues. LLMs are trained with a simple objective: predict the next word in a sentence, repeatedly. By doing that on billions of sentences, they learn grammar, facts, some reasoning patterns, and more. The result is a model that can generate coherent text and be guided to perform tasks via prompting. These LLMs are incredibly versatile. One model can summarize an article, answer questions about trivia, write a short story, or generate programming code just by changing the input prompt. For instance, GPT-3, an earlier OpenAI model, with 175 billion parameters, could do tasks it was never explicitly trained on, like solve simple math word problems or translate from English to French, purely from being prompted. This versatility is exactly why they're foundation. You build specific applications on top of them. We'll see that when we turn a generative model into an agent, we're essentially augmenting it with an interface to the world, tools, memory, etc. But the backbone is still an LLM doing the heavy cognitive lifting, like understanding instructions or composing responses. Now we shift from generative AI to agentic AI. When we say an AI has agency, we mean it can initiate actions towards achieving a goal rather than just responding passively. It has a kind of autonomy. Imagine an AI that not only writes text for you but can click buttons, run programs, fetch data, and so on, all on its own. That's an agent. A generative AI might give you information, but an agentic AI can use that information to do something in the world, even if the world is just the digital world, like calling APIs. Another way to think of it, agentic AI equals generative AI plus decision-making's action-taking capabilities. Usually an agent will have an LLM at its core for reasoning in natural language, but it's augmented with the ability to interact. Maybe there's a module that lets it call APIs, or a context where it can output an action that the system will execute. We give it some goal or permission, and it can decide the steps to take. For example, say you want an AI to be a personal travel assistant. A generative AI like ChatGPT could suggest a travel itinerary if you ask for one. But an agentic AI travel assistant could go further. It could actually search for flights on an airline's website, compare prices, book the flight for you, then book hotels, all via whatever tools it has access to, and then confirm everything with you. It's like the difference between an encyclopedia, which gives you answers, and an employee who can actually do tasks for you. Why do we want agentic AI? Because many problems require action, not just an answer. In data science terms, imagine automating an entire workflow, not only analyzing data, but also sending notifications or updating dashboards automatically based on the analysis. An agent can handle that end to end. Or in business, an agent could automate routine processes. Maybe an AI sales intern that scans the CRM, drafts personalized emails to leads, and sends them, whereas a static GPT model might only draft one email when asked and not remember context. Agentic AI holds the promise of adaptive, goal-driven automation. Instead of rigid scripts, you have AI that can figure out the procedure to accomplish something and then do it. This can save human time on multi-step tasks and handle dynamic situations where we can't predefine every step. It's a big step up in complexity from just generative Q&A, and that's why we're dedicating effort to learn how to design and control these agents. Let's clearly distinguish generative AI from agentic AI with a comparison. A generative AI system is like an advisor that you consult. It gives you information or content, but it's ultimately up to you or some other system to act on it. It operates in a single-turn mode often. You ask, it answers, and that's it. It doesn't remember objectives or carry over state except within the current conversation context. And crucially, it doesn't alter the outside world aside from producing the answer. It's read-only in effect. An agentic AI, on the other hand, is like an autonomous assistant. You give it a goal or problem, and it doesn't just hand you an answer. It can actually take initiative to achieve the goal. It might do multiple things in sequence, refer back to prior information, it has a notion of memory or state across steps, and it can impact the world or the system by writing or executing operations. It's a loop of perceive, decide, act, rather than a straightforward question-answer. For example, ask a generative AI, "What's the weather in Paris tomorrow?" It will probably say, "It's forecast to be 18 degrees and sunny," if it has access to that info or was updated recently. It just informs you. Ask an agentic AI the same thing. If it's properly set up with tools, it might internally decide, "I should check an API." It calls a weather API, one action, gets data, then maybe it decides, user might want this in their calendar and schedules a calendar entry, another action. Or it could simply just do the same as the generative AI and give the info. But the point is, it could do more. Agentic AI works to fulfill your intent, not just answer the literal question. And it could ask clarification questions if needed, or break the task into subtasks. Another angle, Agentic AI incorporates generative AI for its reasoning and communication. Think of the LLM as the agent's mind that can think and speak. But the agent has a body too. That body are the tools or actions it can perform, like clicking a virtual button, calling an API, running code. The generative part and the agentic part are integrated. The LLM decides, should I use a tool? Should I just respond? If using tool, what's the input, etc. It might be literally outputting something like call weather API city Paris in a special format, which the framework executes. Then the LLM gets the result and continues. So agentic systems use generative AI internally, but extend it with an action-taking capability and an iterative loop. In summary, GenAI answers what you asked. Agentic AI figures out what needs to be done, which might include answering and more, and does it. One is static content generation. The other is interactive, stateful decision-making and action. Let's recap large language models briefly since they are central to agentic AI. LLMs like GPT are built using the transformer architecture. That architecture's key innovation was the self-attention mechanism, which allows the model to weigh the relevance of every word in the input with every other word. In practical terms, the model can attend to relevant bits of context, even if they're far apart in the text, solving problems that older RNN models had with long-range dependencies. The transformer is organized in layers. Each layer refines the representation of the sequence by attending and then passing through a feed-forward network. When you stack many layers, like 96 layers in some large models, you get very rich representations. The model ends up with an internal encoding of language that captures syntax, semantics, even some real-world knowledge that was implicit in text. These models are trained on huge amounts of data. For instance, GPT-3's training data was on the order of hundreds of billions of tokens, internet web pages, books, Wikipedia, etc. This broad training gives them a surprisingly wide knowledge base. They effectively compress patterns from all that text into their parameters. So they learn not just language structure but facts, e.g., Paris is the capital of France. How to do certain tasks, to some extent, like translating or code syntax from seeing many examples, and even some reasoning patterns, like how to logically continue a thought. LLMs generate text by predicting what comes next. So when you prompt them, they start churning out words that statistically and semantically seem like a good continuation of what you provided. If you crafted the prompt well, like including a question or an instruction, the continuation will likely be an answer or a completion of that instruction. They do exhibit emergent abilities, meaning when they reached a certain scale, they started to handle tasks they weren't explicitly trained for. For example, GPT-3 can do simple arithmetic or answer trivia, even though it wasn't given an explicit database of math or facts. It picked up the ability from patterns in text. That said, they are not perfect. They can hallucinate. Sometimes the statistically plausible continuation is factually wrong, but it sounds confident and correct. They don't have a grounded understanding of truth. They just know what could be said next. So an LLM might state a wrong year for an event with full confidence because many similar sentences exist with different years, and it picked a likely one. This is a big issue when using them as knowledge sources. They also have a context window limit. Maybe they can only handle 4,000 tokens of input for older models, or up to 100,000 tokens for the latest ones. They can't recall anything beyond that window unless you explicitly feed it again. That's why agents often use external memory or retrieval, like remember this info by saving it somewhere else and reinserting when needed. So in agents, the LLM is fantastic at flexible reasoning and language generation, but it might make stuff up or not know something current. We mitigate that by giving agents tools like web search or structuring prompts to reduce hallucinations. And for context limits, we have strategies like chunking information or summarizing past dialogues. In summary, LLMs equals powerful but imperfect brains. As we build agentic systems, we harness their strengths, language understanding and generation, and compensate for their weaknesses, lack of up-to-date knowledge, tendency to fib, limited memory, through the system design, like using retrieval augmentation and establishing guardrails. Since interacting with LLMs is primarily done through text prompts, prompt engineering has become an important skill. A prompt is basically how we program the model using natural language. Unlike traditional software, we don't write code to configure behavior. We write in English or any language instruction or dialogue that coaxes the model to do what we want. A well-crafted prompt can dramatically improve the quality of output. For example, if you want a summary of a document, a very straightforward prompt might yield a generic summary. But if you prompt with more guidance, like summarize the following text, focusing on the financial outcomes and ignoring background history, you'll get a more targeted summary. We have a few common prompting techniques. Zero-shot prompting. This means you just instruct the model without giving any examples. E.g., translate this sentence to Spanish, followed by the sentence. The model has to do it from its learned capabilities alone. Few-shot prompting. Here you include one or more examples of the task in the prompt itself. For instance, you could write, Q, what is 2 plus 2? A, Q, what is 3 plus 5? 8, what is 7, 6? A. By giving those examples, 2 plus 2 and 3 plus 5, you prime the model to see the pattern, and it will likely answer 13 for 7 plus 6. Few-shot examples basically condition the model to follow a certain pattern or format. This can greatly improve performance on specific tasks, especially if the model has the capability but isn't sure what format you want the answer in. Chain of thought prompting. This is adding something to the prompt that encourages the model to reason step by step. For example, after a question you might add, let's work this out step by step. It's been found that models will then often produce a multi-step reasoning process, which you might see as them talking to themselves, and then conclude with an answer. This often yields more accurate results on math and logic problems because the model is effectively using its own scratch pad to not jump straight to an answer, but work through it. Role specification. You can tell the model to take on a persona or role which can influence style and sometimes content. For instance, you are an expert data scientist, explain X. The output might become more technical and precise because it's following the role cue. Format specification. If you need the answer in a certain format, say it explicitly. Models are surprisingly good at formatting if you ask, e.g., give the answer in JSON or list the steps in bullet points. If not told, they might give a lengthy narrative by default. Providing context or constraints. If the model needs some context it wouldn't otherwise know, like specifics of your company's data, you have to feed that in the prompt. Also, if there are things to avoid or focus on, you mention them. For example, in the response, do not mention any personal data and ensure to include at least one statistic from the text above. It's a bit of trial and error sometimes. You often iterate. If the model output was off, you tweak the prompt, maybe add an example of the desired output, or clarify the instruction. Prompt engineering is critical for agents too. You might have a system prompt that sets the rules, then the agent sees user input. If your system prompt says always explain your reasoning before giving an answer, the agent will do that. If it says only output valid JSON when responding, the agent will try, though not 100% reliably, but usually yes. In summary, think of prompt engineering as guiding the model's behavior with carefully chosen words and examples. It's both science and a bit of art. As these models get better, they often require less coaxing. They understand instructions more readily. But for now, and especially for tricky tasks, how you ask is extremely important. When designing an AI agent, there are different paradigms or architectures we can follow. Each has its pros and cons and use cases. First, reactive agents. These are perhaps the simplest. They just react to the current input or state with an action, without internal deliberation over future steps. In classical AI, we think of subsumption architecture in robotics. Like a robot has a rule, if obstacle detected, turn 90 degrees. There's no long-term planning, it's just responding to stimuli. In our LLM context, a reactive agent might simply take the user's latest request and output an action or answer immediately based on that. It won't think, maybe later I should do something else. It's myopic, focusing on now. Reactive agents are typically robust and fast for straightforward tasks, fewer moving parts, you sense and act. But they struggle with tasks that involve sequential steps or require remembering what happened earlier, since they don't have an internal memory of what's not currently perceived unless you explicitly feed it in every time. Next, deliberative planning agents. These agents do look ahead or reason about a sequence of actions. They maintain some internal state or model of the world, like beliefs about the environment, goals they want to achieve, and can formulate a plan of action. A common model here is the BDI, Belief, Desire, Intention model, which maps well to deliberative agents. Beliefs equals information state, desires as goals, intentions current plan of action. A deliberative agent might say, given what I know, beliefs, and what I want, goal, I'll intend to do X, then Y, then Z. This is more computationally heavy. It might involve search or careful reasoning, but it's powerful for non-trivial tasks. For example, an agent playing chess must plan ahead. A purely reactive approach would be very weak at chess beyond immediate tactics. In LLM agents, we often simulate planning by having the model outline steps in plain language, or we might have a separate planning algorithm, or even a separate LLM that just generates a plan which another LLM executes. Planning agents are needed when an objective can't be achieved in one direct step, or when there are choices to be made about how to approach a problem. The downside is they might be slower, and if the world changes while they're planning, their plan might become suboptimal. So sometimes a mix of reactivity and planning is used. Plan at high level, react at low level. Then tool using agents. We give our agents tools to overcome the innate limitations of the LLM. No matter how well trained, an LLM might not know the temperature in London right now, or the result of a particular database query from your company's server. But if the agent can call a tool, think of a tool as any external function or capability like an API, a database query, a web search, or even executing code, then the agent can retrieve fresh information or perform actions the LLM alone couldn't. In frameworks like LangChain, you explicitly define tools and the agent can choose to invoke them. Tool use is a defining feature of many agent systems. It's how they act on the world. Without tools, an LLM agent is just thinking and talking. With tools, it can say send an email or fetch data. Designing an agent with the right set of tools and prompting it in a way to use them when appropriate is a big part of agent engineering. We saw that one difference between GenAI and Agentic AI is environment interaction. Tools are how we implement that technically. Finally, self-reflective agents. These agents incorporate a feedback loop on their own outputs or decisions. For example, an agent generates a draft answer or takes an action, then it has a phase of reflecting. Was that a good idea? Did that answer actually solve the user's request? If not, it can revise its approach. We sometimes operationalize this as having two LLM calls, one to produce an answer, another to critique it, or using one LLM with a prompt that says, first think of an answer, now critique that answer, now improve it. This is essentially the Evaluator Optimiser pattern we will also mention in patterns. A self-reflective agent might catch mistakes an ordinary agent would miss. For example, maybe the agent gave an answer that contradicts information in a source. A reflection step might notice that inconsistency and correct it. Or in a multi-step plan, a reflection step might notice a plan isn't working and try a different approach. The trade-off is time computation. Reflection means extra cycles, and you have to decide when to stop reflecting and act. In practice, many systems blend these architectural ideas. Tool use can be present in any of those, reactive tool use or planned tool sequences. So these terms, reactive, deliberative, tool using, reflective, are conceptual lenses. They help us think about designing agent behavior. For a simple task, a reactive approach might suffice. For a complex task, you likely need a planning or reflective approach. For tasks requiring outside info or actions, you definitely need tool use. Understanding these helps us choose the right approach or combination for a given problem. So far, we talked about a single agent. But what if we have many agents? That's a multi-agent system, or MAS. It's a system where not one but multiple autonomous agents are present, and they usually can interact with each other. This opens up a new dimension because now agents could potentially work together to solve a problem. Or in some cases, they might even be in competition. Imagine a market simulation with buyer agents and seller agents, each trying to get the best deal. That's a multi-agent scenario with competing objectives. Why use multiple agents instead of one big agent? There are a few reasons. Parallelism. If you have subtasks that can be done in parallel, multiple agents can speed things up. For example, if you need to analyze data from 5 different sources, you could spawn 5 agent processes to do them simultaneously rather than one agent doing them sequentially. Specialization. You might want different agents to specialize in different roles or types of reasoning. One agent could be really good at planning but not at coding. Another could be good at coding. Or one agent might be the idea generator and another the critic. By having multiple agents with specialized prompts or models, you can leverage their strengths together. A clear example, in the software agent team idea, you could have a manager agent that breaks a feature into tasks, a coder agent that writes code, and a tester agent that checks the code. Each is specialized, and when they communicate, manager gives tasks to coder, coder gives code to tester, tester reports bugs back. Together they accomplish something bigger. Modularity and emergent behavior. Sometimes splitting into agents can simplify design. Each agent can be simpler and complex behavior emerges from their interaction. Also, you might observe emergent solutions when agents brainstorm together or argue different viewpoints. Anthropic had research where 2 Claude instances discussed to come to a better answer than either alone, the principle being that collaboration or debate can yield better results. Communication is key in mass. Agents need to coordinate. Who is doing what? What information do I have that others need? When am I done so I can hand over to the next agent? This is where protocols come in, essentially the rules format of agent communication. A simple protocol could be manager sends tasks, worker acknowledges, worker sends result, manager verifies, done. Or a bidding protocol, one agent asks for proposals, others respond, one is chosen. In human organizations, we have meeting protocols, email etiquette, etc. Similarly, for agents, we often use structured messages. In practice with LLMs, sometimes they just talk in plain English to each other. That can work too, albeit with less guarantee they won't go off script. But there are standards like FIPA ACL, Agent Communication Language, that define message types formally, e.g. inform, request. In an LLM mass, maybe we instruct them to prefix messages with some labels like Agent 1 to Agent 2, content, to keep track. Examples of mass. One example I gave, an AI software development team where each agent has a role in the development pipeline. Another, which is quite relevant, AutoGPT and similar projects basically spawn multiple sub-agents. Early AutoGPT had an agent that could spawn a new instance of itself to tackle subtasks, or have a critic agent that critiques the solver agent, etc. Simulations. If you want to simulate, say, a market or a social scenario, you can have multiple agents each representing an actor. This has been done for research. Stanford had a paper where they put multiple agents in a simulated town with memory and personality to see how they interact, and they ended up planning a Valentine's Day party spontaneously. It's fascinating because it was emergent from multiple agents, each acting independently but socially. When agents cooperate, a concept of shared environment or shared goals comes in. They might model not just the environment but also each other's mental states. I, as Agent A, might have a belief about what Agent B knows or intends. This can get complex, game theory, etc., if competitive. But also synergy. One agent can do something that helps another, like one agent might gather information that a second agent then uses to make a decision. It's worth noting, though, having multiple agents also increases complexity and risk of something going wrong. They might miscommunicate, or you get circular behavior where agents A and B keep asking each other the same thing. So mass design typically needs careful thought on how to avoid deadlocks, ensure messages converge to decisions, etc. We'll delve into patterns that involve multiple agents later, like how to structure Orchestrator versus workers, etc. But big picture, multi-agent systems can be very powerful in breaking down tasks and mimicking teamwork or multi-actor environments. In data science tasks, you might not always need multiple agents, but in large-scale or complex projects, You might assign different responsibilities to different agents to make the problem tractable. Drilling down on communication and the BDI model in multi-agent systems. When agents communicate, it's not just chit-chat. Typically, it's purposeful exchange of information or requests. In multi-agent systems research, a lot of emphasis was put on developing formal agent communication languages and protocols so that systems could be predictable and even allow heterogeneous agents, maybe written by different parties, to talk to each other. One standard I mentioned is FIPA ACL, which defines performatives like inform, request, propose, accept, reject, etc. For example, an agent might send a message like request sender agent 1, receiver agent 2 content, perform action X. Agent 2 might reply with agree or refuse, or after doing it, send inform content I did X. This structured approach helps avoid ambiguity. However, in LLM-based agents, since they operate in natural language, we sometimes just let them speak English to each other. That's flexible, but can be less reliable. They might go off track. So some work is being done on making LLM agents stick to a more structured communication format, like JSON messages or explicit function call formats, while still leveraging the natural language understanding of the LLM to fill in the content. The slide also mentions that communication can either be direct messages, like one agent sends directly to another, or indirect via environment. Indirect means maybe they're both connected to a shared database or Blackboard. One agent writes something there, another later reads it. For example, in robotics, one robot might leave a marker in the environment that another senses. In our digital scenario, indirect could be writing to a shared file or memory that others check. Now, the BDI model. This is a conceptual framework that's useful to think about how agents reason, especially in a multi-agent context. It was inspired by practical reasoning in humans, Michael Bratman's philosophy on intentions, etc., turned into an AI model by Rao and Georgiev, etc. In BDI, beliefs, what the agent believes about the world. This includes facts it's observed or learned. In a mass, beliefs could include the agent's beliefs about other agents, states or capabilities, e.g. Agent A believes Agent B is busy or that Agent B has already completed Task 1. Beliefs get updated by communication. If Agent B sends a message, Task 1 done, Agent A updates its belief that Task 1 is done. Desires, what the agent wants to achieve. An agent can have multiple desires. Some might conflict or not all can be achieved. They represent possibilities, not all of which the agent will act on. For example, an agent might desire to finish its project and also desire to minimize cost, and also desire to help another agent. It may not achieve all, but those are motivations. Intentions, the subset of desires the agent has committed to act on, i.e., chosen as its current goals, and the plans it has adopted to achieve them. Intentions lead to actions. If an agent adopts an intention, it means I'm going to do X unless I reconsider later. So, bridging to multi-agent, agents might negotiate or communicate to reconcile their intentions. Like Agent A might desire that a report is written, Agent B desires the same outcome. They talk and decide, form intention, that A will gather data and B will write the report. After the discussion, Agent A's intention, collect data by time T, and Agent B's intention, use data to draft report, for example. In multi-agent interactions, BDI can be useful. For instance, Agent A believes it has high workload, desires to delegate something. Agent B believes it has some free capacity. A might request B to do a subtask. A is basically revealing a desire or intention that some task be done and proposing B does it. B then updates belief, A wants me to do X. If B's desires include being cooperative or if X aligns with B's goals, B might form the intention to do X and reply, yes, I will do X, communicating that intention to A. Now A updates belief that B intends to do X, so A can drop that desire from its own list. A doesn't need to worry about X now. That's a lot of mental simulation, but it shows how communication serves to align the beliefs and intentions of agents so they can coordinate. Without communication, each agent can only guess what the others are doing. One more piece. When agents communicate in natural language, we often interpret utterances in BDI terms. For example, if Agent A says, I will handle data collection, that's essentially A expressing an intention and informing others of it. If B says, do you need help with analysis, B is expressing a desire or at least a query to understand if it should form an intention to help. We can map these to performatives like propose or offer. The synergy is a well-designed agent communication protocol paired with a BDI reasoning cycle allows a mass to reach agreements, divide tasks, and update each other's knowledge systematically. This is how, say, contract net protocol for task allocation works in BDI terms. A manager agent broadcasts a desire for a task to be done, worker agents receive it, and if they desire to get the reward they might intend to bid, etc. Eventually one is selected, and both manager and that worker lock in the intention that worker will do task, while others drop it. So BDI is a powerful abstraction for thinking about multi-agent coordination and how communication updates what agents think and do. In our LLM world, we don't have explicit BDI modules, though interestingly some researchers talk about implementing BDI with LLMs by having it maintain a belief database, etc. But even implicitly, when we design prompts or flows, we might consider an agent's beliefs, maybe store memory, its goals, maybe given by the user or set as system instructions, and having it commit to a plan of action, which we see when an agent picks a tool to use. That's like an intention being executed. The ecosystem for building LLM-driven agents is evolving rapidly. We have several frameworks and tools that make it easier to create these agents without coding everything from scratch. Let's highlight a few. LangChain. This is one of the most widely used libraries in the LLM app dev space. Think of LangChain as a Lego set for LLM applications. It provides abstractions like chains, sequences of operations involving LLMs, and agents, which are essentially LLMs with tool usabilities. With LangChain, you can define a set of tools like a calculator, web search, database query, and then initialize an agent that uses an LLM to decide how and when to use those tools. LangChain handles the loop of taking the LLM's output and either executing a tool or returning the final answer. It also has memory components to store conversation context beyond one turn, so your agent can remember earlier interactions, embedding in or just storing raw text. For example, in code you might do LLM equals OpenAI model GPT-4, tools, calculator, SERP API, agent, equals initialize agent tools, LLM, agent type.0 shot React description, result agent.run, what was the revenue last quarter and what is 20% of that? And it will figure out it needs to maybe query some database for revenue if that was a tool, then do calculation, etc. LangChain basically simplifies hooking up these pieces. It's quite flexible, supports multiple LLMs, and it's open source, Python and JavaScript. AutoGen by Microsoft Research. AutoGen is more specialized for multi-agent dialogues. It lets you define multiple agents, like say one agent as the system, one as the user, or two AI agents that talk to solve a problem, and handles the message passing between them. You can set different personas or capabilities for each. It also supports tools. AutoGen came from research that showed how agents can collaborate to solve complex tasks. The supply chain optimization example, they had like a planner agent and executor agent interacting. So if you want to prototype something like AI lawyer versus AI judge debating a case, AutoGen could be handy. You'd spin up a lawyer agent, a judge agent, and let them converse according to rules you give. It's a bit lower level than LangChain in that you might have to orchestrate the conversation loop yourself, but it provides the structure for multi-agent chat. Also, being from MSR, it integrates well if you want to use OpenAI's Azure endpoints, etc. crewAI. This framework is newer and geared towards orchestrating a group or crew of agents working on a task together. It emphasizes structured multi-agent workflows. For example, you can specify a pipeline where Agent 1 outputs goes to Agent 2, etc., or a hierarchy, like manager sub-agents. crewAI introduced the notion of a task object for clarity, so each agent knows exactly what type of task it is allowed or expected to do. It also has robust memory features, embedding-based long-term memory. I recall an example where they used crewAI to optimize a retail shelf layout. One agent analyzed inventory, one agent suggested layout changes, one agent evaluated the plan, etc. The crewAI framework managed that conversation and tool usage. So if you want to implement a scenario with, say, 3 specialist agents handing off work, crewAI provides patterns for that. Hugging Face Transformers agents / small agents. Hugging Face has both a concept called Transformers Agent and a library named Small AI or Small Agents. The idea is to bring agent capabilities to the Hugging Face ecosystem. They allow you to use open source models, so you're not locked to OpenAI or proprietary ones, and still give them tool use. For instance, Hugging Face demonstrated an agent that could pick the right model from the hub to do a task, like it might call a specific model for image generation if asked for an image, or call a text model for Q&A. This is interesting. It's like a meta agent picking models as tools. Small Agents, specifically, is designed to be a minimalistic agent framework focusing on ease and safety. It might not have all bells and whistles, but is lean. The integration with Hugging Face's Inference API also means you can run pretty powerful models, like maybe you use Big Science's Bloom or Meta's Llama 2 as the LLM. Hugging Face's courses and examples show how to do multi-agent orchestration too, like that multi-agent web browser example we saw, where a manager agent uses a search agent. Llama Index, formerly GPT Index, this is slightly different. It's about connecting LLMs to external data, documents, SQL, etc. It's not an agent framework per se, but it's often used inside agents to provide a memory or knowledge-based tool. If you build an agent that needs to answer questions about a set of documents, you'd use Llama Index to index those docs and provide a query interface. The agent then calls that as a tool, like user asks something. Agent queries the index for relevant info, then uses it to compose an answer. So Llama Index is a very useful component in the agent developer's toolkit to overcome the LLM's knowledge cutoff or limited context by allowing retrieval of relevant info on the fly. OpenAI's function calling and swarm. Most recently, OpenAI models allow you to define functions that the model can call with JSON arguments. That's how you enable tool use in a structured way with models like GPT-4. You basically say, here are functions like get weather, search news, etc. And if the model decides it needs them, it will output a JSON object calling them. The developer code will execute it and return the result to the model. This is not a full framework, but it's a built-in mechanism now that is widely used to make agents with OpenAI's API. OpenAI's Swarm we discussed. It's an experimental mini-framework for multi-agent orchestration where they emphasize the concept of handoff. One agent can pass control to another via function calls. It's more for exploration and education at this point than production, but it indicates the direction things are going, making multi-agent orchestration easier and more standardized. There are also specialized frameworks for particular domains. E.g., IBM has one called BAI mentioned in their docs for contract management. Meta has Cicero for negotiation, which combined an LLM with planning for playing diplomacy game, etc. But LangChain, AutoGen, crewAI, and the toolkits around them cover a lot of general needs. The good news is, you don't have to build from scratch. The more challenging news, there are many choices, and part of being an engineer here is picking the right tool for the job and learning its abstractions. As we got deeper into building agent systems, a number of design patterns have emerged. These are essentially standard ways to organize agents or agent steps to solve common problems. Patterns help us because they're like templates or best practices. You don't always want to reinvent how agents coordinate for every new project. You can often apply a pattern that others have used successfully. On this slide, I've listed a few key patterns that we're going to go through one by one. 1. Orchestrator worker pattern. This is basically the manager-worker concept. One agent acts as a coordinator or planner and delegates chunks of the task to one or more worker agents, then consolidates the results. We briefly mentioned it earlier in examples. It's like having a boss agent that splits a project and the team members do parts. This pattern is very common when dealing with complex tasks that naturally subdivide. 2. Router pattern. Here an agent's main job is to decide who or what should handle an incoming query. It's like an AI traffic cop or dispatcher. For example, a router might detect the category of a user request and then forward it to a specialist agent or workflow. This pattern is about specialization and gating, e.g., route simple requests to a FAQ agent versus complex ones to a research agent. 3. Evaluator Optimiser pattern, reflection. This involves two roles, one that generates a solution, the Optimiser generator, and one that evaluates that solution and provides feedback, the evaluator, or critic. They usually work in a loop or a back and forth until the result is good enough. We also call this reflect and refine, or sometimes reflection, after a research paper name. This pattern is great for improving quality and catching errors by essentially having the AI double-check or iterate on its outputs. 4. Parallel agents pattern. Instead of sequential or one-by-one execution, you spin up multiple agents to work simultaneously and later merge their outputs. This might be used for speed, to handle multiple user queries at once, or to handle parts of a task concurrently, or for diversity of thought. Have 5 agents propose solutions and then pick the best. We'll talk about how you then aggregate, maybe with a vote or a judge agent. Number 5. Human-in-the-loop pattern. As much as we automate, sometimes a human needs to be part of the process. This pattern explicitly includes human oversight or input at certain steps. For instance, an agent might draft an email, but a human approves it before sending. Or an agent might ask the user a clarifying question in the middle of a long workflow. We design these points intentionally for safety or guidance. Each of these addresses common needs. Orchestrator workers equals dealing with complexity via divide and conquer. Router, dealing with variety of tasks by specialization. Evaluator Optimiser, addressing quality assurance and iterative improvement. Parallelization, addressing performance, time, or reliability through redundancy. Human in loops, addressing safety, accountability, or simply tasks AI can't handle well alone. We'll go into each pattern in the next slides with an illustration or scenario so you can see how they work in practice. Let's dive into the orchestrator worker pattern. This is probably the most intuitive if you think in terms of a team with a leader. How it works: you have a central agent, the orchestrator, which is responsible for understanding the overall goal and breaking it down. Then you have one or more worker agents, each capable of executing some part of the task. The orchestrator basically does task planning and assignment, and the workers do task execution. In a step-by-step scenario, 1. The orchestrator gets an input or a goal, for example, prepare a quarterly business report. 2. The orchestrator agent thinks, okay, to do that I need financial data analysis, market research, and drafting the report. It decides those are subtasks. 3. The orchestrator then says, worker A, you handle financial data analysis. Worker B, you handle market research. Worker C, you draft the report once A and B give you their pieces. This is the orchestrator splitting the task and assigning. In an LLM system, this could be done by the orchestrator sending specific prompts to each worker agent, like it might formulate a message, at worker A, please analyze revenue and profit for Q3 and summarize key changes. 4. The workers do their jobs. They might do them in parallel if the system allows or in whatever sequence orchestrator decided. They might have their own tools, e.g., worker A might use a database query tool, worker B might use a web search tool. 5. Each worker sends back their result to the orchestrator. 6. The orchestrator waits until it has all pieces, or it might have a logic to proceed as results come in. Then it integrates them. In this example, orchestrator agent might take the analysis summary and market research info and then either pass it to another agent to format, or maybe orchestrator itself drafts the final combined report. Sometimes the orchestrator itself might just be a coordinator, and you might have a specific assembler agent. But typically, orchestrator can do the merge or ask one of the workers to do it. Use cases. This pattern shines when tasks are decomposable. Some real or hypothetical examples. A data science workflow. Orchestrator agent says we need to do ETL, then analysis, then visualization. It assigns an ETL agent to do data cleaning, a modeling agent to run analysis, and a report agent to make a chart. Or think of an ML pipeline. Orchestrator might spawn an agent to do feature engineering, another to train different models, another to evaluate them. Software dev. Orchestrator breaks a feature into subcomponents. Each coder agent handles one, etc. Customer service automation. Orchestrator classifies a customer issue and might engage multiple bots. One bot pulls customer data, another formulates solution steps, then orchestrator compiles a response. Benefits. It's scalable in that you can add more workers for more subtasks pretty easily, or parallelize heavy tasks across multiple workers. Specialization. Each worker can be tailored. For example, if part of the task is writing Python code, You might have a worker prompt or configuration that makes it very good at coding. If another part is writing a summary, maybe that worker uses a different model or prompt geared for summarization. The orchestrator is like the generalist who knows a bit of everything to plan, but workers are specialists. Maintain coherence. The orchestrator overseeing everything helps keep the final output unified. Without it, if workers just independently did stuff, you might get disjointed results. The orchestrator can ensure, okay, we have analysis and research that are consistent, now the report is cohesive. Challenges. Single point of failure. If the orchestrator misplans or assigns wrongly, the whole thing can flop. If it breaks tasks incorrectly, e.g. misses a subtask or assigns to a wrong agent, the outcome suffers. So the orchestrator agent needs to be fairly reliable. Task allocation. Non-trivial at times. How does the orchestrator decide which agent gets which subtask? In our case, we often hardcode roles, like we know worker A's purpose, but in general, if multiple workers could do similar tasks, orchestrator might need a strategy to choose who, maybe based on availability or expertise. This starts to sound like multi-agent scheduling problem, which is complex. Interdependencies. If subtasks depend on each other, like worker C needed outputs from A and B before it can start, orchestrator must manage that ordering. It might have to implement some synchronization, e.g., only tell worker C to start once A and B are done. Or maybe orchestrator gave an instruction to worker C that said, wait for the data from A and B, but how does worker C know when to actually proceed? Typically, orchestrator collects A and B, then explicitly provides them to C. So orchestrator might have to do another round of communication. After A and B reply, send a consolidated message to C. Complexity. The orchestrator is doing heavy lifting in terms of decision logic. If tasks are very dynamically changing, the orchestrator's job becomes tough. Imagine midway a subtask result suggests the need for an additional subtask. Orchestrator has to adapt and maybe spawn another agent or reassign. In practice, many frameworks, like crewAI or the example in Arise comparison, support this pattern naturally. For instance, crewAI was noted to work well for hierarchical structures, which is exactly this pattern. To visualize, if you think back to the earlier mention in LangChain docs, they have an agent executor, which is basically orchestrator logic, and sometimes that agent can call other chains as if they were sub-agents, though typically LangChain's agent is a single LLM that could solve subtasks by tool calls rather than fully separate agents. This pattern has shown up historically too, e.g., in the 90s, the Blackboard system concept, where different specialist knowledge sources, like our workers, contribute to a Blackboard, the orchestrator environment, where a control agent decides which knowledge source to invoke next. It's analogous. So orchestrator worker is a fundamental and widely useful pattern for agentic systems. The router pattern is about having an agent that doesn't itself solve the problem fully, but directs the problem to the right solver. It's like calling a customer service line, and the automated system says, press 1 for sales, 2 for support. The automated system is routing you to the department agent you need. In our case, the LLM router is smarter. It reads or understands the request and decides which specialist agent or predefined chain should handle it. How it works. The router agent receives the user's query or task description. It uses either a prompt-based classification, given this input, which category does it fall into, or some embedded logic, maybe a prompt that has instructions like, if the query is about coding, output code, if about math, output math, if about something else, output other. Possibly it could also incorporate external classifiers or rules. Once it determines the category or the intent, it forwards the query to the corresponding specialist agent or template. For example, if it determined category account balance question, it sends it to the finance bot agent. If it determined technical troubleshooting, send a tech support agent. Optionally, the router might reformat the query or add some context for the target agent. Like it might call the agent with a message, user is asking about X, classified as category Y. Here is the question. To give the agent context that was classified as Y. Use case example. Imagine a multi-skill virtual assistant for a company that can answer HR questions, IT support questions, and general knowledge. Rather than making one giant agent to handle all of that, which could be complex to prompt or fine-tune, we could have HR agent trained or prompted on HR policy, benefits, etc. IT agent knows about technical support, password resets, etc. General agent knows general knowledge or default fallback. Then we have a router agent that first looks at the user's question, how do I reset my email password? Router sees keywords or based on prompt thinks this is IT support, so it forwards to IT agent. Another question, what's our company holiday policy? Router forwards to HR agent. This way, each agent can be optimized for its domain. You could even use different models for different agents. Maybe HR agent uses a smaller model, fine-tuned on HR data. IT agent uses a larger model if needed for complex troubleshooting. The router just needs to be good at classification. LangChain actually has a chain called a multi-prompt chain, or a router chain, that does similar. It picks among multiple candidate prompts or chains using an LLM to decide. Patronus AI had a blog on best practices for LLM routing, and the idea of using an LLM as a router has been around, because it can parse user intent from free text pretty well, like better than writing regexes for it. For example, you provide the router with descriptions. Agent A can handle math and will output calculations. Agent B can handle personal advice. Agent C can handle medical questions. And you ask the router which is best. The router LLM will output something like route to Agent A if the question looks mathy. Benefits. Each specialist agent can be smaller, simpler, because it only focuses on one area or task format. If you need to update one domain, like add a new specialty, you can plug in a new agent and update router logic without retraining a huge unified model. It can also be more efficient. If router can direct simple queries to a lightweight agent, maybe a rules-based FAQ, but heavy ones to a powerful agent only when needed, you save resources. This is like using smaller model for easy tasks, big model for hard tasks. Maintains better quality since specialized models or prompts may perform better on their niche tasks than one general prompt that tries to cover everything. Challenges. The router can make a mistake, just like an email spam filter can misclassify. If it sends a query to the wrong agent, the user could get a wrong kind of answer. Imagine it routes a legal question to a medical agent. Could be nonsense. So the router needs to be pretty accurate. This might require careful prompt engineering for the router, or even fine-tuning a classifier model to assist it. If a query legitimately spans multiple areas, router might not handle that well. E.g., my paycheck is incorrect after my transfer to a new office. Who fixes this? Is partly HR, paycheck? Partly maybe IT, if it's a system error. A simple router might have trouble. You might need logic to either pick the most relevant or have the agents collaborate. Router patterns often assume one best route. Implementation complexity. You have to maintain multiple agents and the routing logic. If your number of specialized areas grows, the router might become a big multi-class classification problem. But at least it's all in one place. In practice, we often implement router logic within a single LLM by giving it a list of possible options and asking which is best, like multiple choice. This leverages the LLM's understanding. For example, the user request is options. A, code assistant if query about programming, calc agent if query requires calculation, chat agent, general conversation. Which option fits best? The model might answer A in a well-trained case if it sees programming context. So the router pattern is great for systems that need to handle wide variety. It's like triaging, and it's widely used. Think of Alexa's skill routing. They had an interaction model that routes voice commands to different skills based on invocation phrases, or Google's Dialogflow mega agent that can route to sub-agents based on intent recognition. In an enterprise setting, as I said, different departments or knowledge bases. Now the Evaluator Optimiser pattern, which is essentially about iterative improvement with feedback. You can think of this like a writer and an editor working together on an article. The writer writes a draft, the editor reviews and marks corrections, then the writer, or maybe another writer, revises it, and they loop until the piece is polished. In AI agents, one LLM can play the role of generator, and another, or the same one with a different prompt, plays the role of evaluator. How it works in steps. 1. The Optimiser generator agent produces an initial solution to the task. For instance, if the task is solve this math word problem, the optimizer gives an answer, maybe with reasoning steps. 2. The evaluator agent then looks at that output and checks it. It might have specific criteria given. For a math problem, criterion is just, is the answer correct? Maybe it knows the correct answer or can derive it separately. For a code generation task, the evaluator might actually run tests or static analysis on the code. For an essay, the evaluator might check if it addresses all parts of the prompt, or if it's well structured, or if it has factual inaccuracies by cross-checking references. The evaluator then produces feedback. This could be explicit suggestions. The answer seems to miss explanation of X, and result appears off because Y, or it could be a simple score or judgment, incorrect because you assumed. 3. Using that feedback, either the original generator agent or a separate optimizer agent then revises the solution. In many setups, it's the same agent, but now with feedback appended to its prompt. E.g., your previous answer was found to have these issues. Please revise and correct them. It then outputs a second attempt better addressing the points raised. 4. This cycle can repeat a few times. Ideally, after some iteration, the evaluator says, looks good now, or at least we have a much improved answer. We often have a max number of iterations, say 3 or 5, to avoid going forever. Or we stop when the evaluator's critique is trivial or it says solution meets all requirements. Use cases: code generation and debugging. One agent writes code for a task. The evaluator agent runs the code against some tests, or at least checks syntax and finds errors. It feeds back error messages or failing test cases. The coder agent then fixes the code. They loop until tests pass. This is exactly how some automated code assistants work. OpenAI codecs used in an eval context, like passing unit tests with multiple attempts. Math logic problems. The generator tries an answer. Evaluator, which could be the same LLM using a known formula or external solver, checks it. If it's wrong, instruct generator to try a different reasoning approach. E.g., self-refined paper by Madan et al. Had an LLM solve a question, then use the same LLM to reflect and identify errors in its solution, then fix it. This often improves accuracy because the second pass can catch what the first pass missed. Long-form QA or writing tasks. Suppose an agent writes a summary of a document. The evaluator could verify if all key points from the doc are present and no irrelevant info or hallucination. If it finds omissions or inaccuracies, it tells the generator to fix that. For creative writing, evaluator might enforce style or tone, etc. Plan verification. In a multi-step plan scenario, after the agent plans actions, an evaluator agent might simulate or analyze if the plan might fail or violate constraints, then ask for plan adjustments. Benefits. Quality improvement. Instead of taking the first draft the AI gives, which might be okay but not great, this pattern systematically improves it. An experiment in research showed that even using the same model as both generator and evaluator in a loop can self-improve answers, sometimes reaching much higher correctness than one shot. Error correction. If the evaluator can catch factual errors or logical inconsistencies, we reduce inaccuracies significantly. This is one approach to reducing hallucination. Have a second agent fact-check the first agent's answer against a reference source. Adherence to requirements. If the task had specific instructions like use at most 3 sentences or include a quote from the text, the evaluator can enforce those and say your answer has 5 sentences, reduce it, or you forgot to include a quote. Then the final output is more likely to meet all the user's or system's requirements. Challenges. It doubles or more the computational cost because you're running the model for evaluation steps too and possibly multiple iterations. It relies on the evaluator being reliable. If the evaluator agent is not perfect, it might give bad advice. For example, a flawed evaluator might incorrectly say an actually correct answer is wrong, leading the generator to possibly change it to a wrong answer. So ideally, the evaluator agent might need to be tuned or specialized for that domain of evaluation. Maybe even a different model, like a smaller model fine-tuned to be a classifier or so. Diminishing returns. Often after 1 or 2 iterations, things are improved. Doing too many can waste time or even confuse the solution. The agent might start oscillating or adding unnecessary stuff to please the evaluator. Need a stop condition. How do we know when to stop? We can say stop after n iterations, or stop when Evaluator says it's good, but if Evaluator is an LLM saying looks good, can be part of the prompt pattern to stop. Or you could have a quality threshold if you have a quantitative metric. Usually, it's manual, like either a fixed count, or if Evaluator's only feedback are minor nits, you stop. Risk of overcorrecting. Sometimes an evaluator might push a solution in a weird direction, or remove all creativity in pursuit of technical correctness. So you have to balance, maybe weighting different evaluation criteria carefully, like don't optimize so hard for correctness that the answer becomes overly verbose or loses style. We have actually seen commercial systems quietly doing this. For instance, ChatGPT, when it outputs an answer, might have done an internal check to see if it followed the formatting. OpenAI has some invisible prompt tricks for chain of thought and self-evaluation before finalizing an answer. So, Evaluator Optimiser pattern is like having a built-in editor. It's a very powerful approach to get more reliable outputs from AI. We just need to manage the overhead and make sure the evaluation criteria encapsulate what we care about and not something that could be misled. The parallelization pattern is fairly straightforward. Instead of doing things one after another, do them at the same time when possible. This is especially useful for tasks that can be separated into independent chunks, or when you want multiple tries at something to increase odds of success. How it works. If it's a data or workload partition scenario, you break the input data or tasks into pieces. For instance, you need to analyze 100 documents. Give 50 to Agent A and 50 to Agent B concurrently, rather than Agent A doing all 100 sequentially. Or if it's multiple attempts scenario, you create, say, 5 identical agents, or same agent with different randomness seeds or slight prompt variations, and have all 5 try to answer the same question or solve the same problem in parallel. Launch those as separate processes or threads or API calls. They each do their job simultaneously, assuming you have the compute resources. You then have to aggregate results. In data partition case, aggregation might be straightforward, like just combine the outputs, concatenate processed data, or merge analyses. In multiple attempts case, aggregation is more like selection. Pick the best output among them. You might have a separate judge agent to do that. Or a deterministic metric, like maybe the shortest answer if brevity is valued, or if it's code, run tests on each and see which passes. Another type, if they were solving different subtasks, like Orchestrator pattern but done in parallel instead of waiting sequentially, the Orchestrator can gather all subresults when done. That's like a parallelized Orchestrator workers variant. Examples: a question answering system where time is critical might run 2 agents with different approaches. One might retrieve info from a wiki, another from news, and whichever returns an answer first or better is used. Or one might be a fast but less accurate model, and another a slow but more accurate one. Maybe you take whichever finishes by a certain time. Some ensemble strategies do that. Running multiple generations to then do something like majority voting for the final answer. The idea that if 3 out of 5 answers from model agree on something, it's likely correct. This can improve factual accuracy somewhat because random errors might be outvoted. In coding, you could generate multiple different code solutions in parallel and test them all to see which is efficient or passes tests fastest. In simulation or creative tasks, multiple agents could simulate different actors at the same time. That's like multi-agent environment simulation, which is parallel naturally. Data-wise, as mentioned, chunk a big text or dataset for summarization or processing. If each chunk can be done independently, spin up multiple LLM instances to do them concurrently. After that, maybe one agent merges the summaries into an overall summary. Benefits: speed. If you have the hardware, doing parts in parallel can reduce the overall wall clock time. E.g., summarizing 10 documents on 10 agents at once could be nearly 10x faster than doing sequentially. Reliability and quality through diversity. If you do the redundancy approach, like multiple attempts, you hedge against a single failure. If one agent hallucinates or gets it wrong, maybe another got it right. By having a judging step, you can pick the correct one. This works especially if errors are random and independent. Scalability. You can linearly scale up to bigger tasks if you can just spawn more agents, useful in large-scale deployments, like serving multiple user queries truly concurrently, though that's more about throughput, but it's parallel in another sense. Challenges: aggregation overhead. Sometimes combining outputs is easy, like merging sorted lists or something, but other times it's not. For instance, if each parallel agent wrote a chapter of a report, the writing style might differ and the final combined report might be inconsistent. You may need an editing pass to smooth it out. Another example: if multiple agents answered the same question differently, deciding which answer is best might require a complex evaluation. What if each answer has parts of the truth? Then a judge agent might have to synthesize a new answer out of them, which is another layer of complexity. Resource usage. Running in parallel uses more memory compute concurrently. If you only have one GPU, you might not benefit unless you can run multiple smaller models at once or your infrastructure supports it. There's cost considerations too. If using API calls, doing 5 calls in parallel costs 5x one call. Coordination complexity. You need a mechanism, like multi-threading or async calls or distributed tasks, to handle parallel agent execution and then gathering results. If your environment is a Jupyter notebook with synchronous calls, it might be non-trivial to truly parallelize without additional libraries. In something like Ray or Celery, you could dispatch tasks concurrently, but it adds engineering overhead. Potential duplicates, contradictions. If it's redundant attempts, you might waste effort. 4 out of 5 attempts might be essentially wasted if one good attempt was enough, but you did them to ensure one is good. If attempts conflict, you then manage conflict resolution. Parallel write conflict. If agents are writing to a shared resource or environment simultaneously, you need to handle that, like concurrency issues. For example, if 2 agents are both trying to update a database at once, could have issues, though usually our LLM agent tasks are fairly isolated. A good example scenario: a content moderation pipeline might run multiple specialized classifiers in parallel, one for hate speech, one for violence, one for self-harm content detection, on a piece of text so that you quickly get all categories flagged at once. That's parallel usage of multiple agents or models for different facets. In summary, parallelization is often a straightforward pattern but requires some infrastructure to do right, and you have to plan how to assemble the parallel results. But it's very powerful in terms of performance and sometimes quality via ensemble effects. Finally, let's cover the human-in-the-loop pattern. This pattern acknowledges that fully autonomous AI is sometimes not desirable or safe, and that involving a human at certain points is valuable. Rather than an agent system running start to finish on its own, we design it such that a human, could be the end user or a specialist, is consulted or asked to approve at key junctures. How it typically works. We define certain steps or conditions where the AI should yield control to a human. For example, if the agent is about to send an email to all customers, require human approval, or if the agent's confidence is below X on an answer, ask a human to verify or provide the answer. When the agent reaches that point, it might present the current information or decision for human review. This could be through an interface, e.g., the agent prepares an output, but instead of delivering it, it shows a draft to a human with options to edit or approve. The human then either provides input, maybe correct the answer, or choose an option, or just a simple yes/no. The agent receives that and continues the process. For instance, if human approved the draft, the agent proceeds to send it or consider the task done. If the human modified it, the agent might take those modifications and incorporate them into continuing actions, like now it knows the correct info. If the human said, "No, don't do this action," the agent might halt or try an alternative strategy if available. Use cases. Safety-critical tasks, e.g., an agent controlling a physical system, drones, factory controls, might have a human supervise unusual actions. Or a medical diagnosis agent might provide a recommendation, but a doctor must sign off. Customer interaction. Many companies use AI to draft responses, but a human support rep approves send them. This ensures no wildly off message goes out to customers. Moderation. Maybe an AI filters content, but borderline cases are sent to a human moderator to decide. Training and trust building. Initially, keep a human in loop for an AI system in deployment until it has proven reliable. Over time, maybe the human just spot checks occasionally. Human in loop for improvement. Humans can feed corrections back into the system's learning loop. Like reinforcement learning with human feedback is essentially a human in loop training pattern at scale. Benefits: quality control and safety. The obvious one: a human can catch mistakes or ethical issues the AI agent missed. For example, if an agent answer has a subtle error or potentially problematic phrasing, a human can catch that and correct it, preventing any negative outcome that a fully automated system might have caused. Handling ambiguity. AI might be unsure or not equipped to make certain judgment calls. A human can bring real-world context or ethical judgment that's hard for AI. E.g., if an agent is planning to do something unusual, a human can consider factors AI might not, like PR impact, legal issues, etc. Learning from human feedback. Each human intervention can be used as a feedback to make the AI better next time, if we log those and incorporate in retraining. Even if not, the system performance is effectively boosted because when AI was weak, human filled the gap. User trust. Having a human oversee critical steps might make end users or regulators more comfortable that there's accountability and that it's not an unchecked AI making decisions. The AI will draft your investment plan, but a certified financial advisor will review it before it's sent to you. Challenges: speed, scalability. A human in the loop is a bottleneck. It could break the automation promise if humans have to intervene too often. If volume is large, you need enough humans. If response time matters, waiting for a human can slow things down drastically, like you can't have real-time interactions if a human has to step in and they're busy. Human workload and attention. If the AI isn't very accurate or is too cautious, it might ask humans too frequently. Alert fatigue. Humans might start rubber stamping without proper review if there are too many checks. We have to calibrate so that humans are involved only when necessary or at a manageable frequency. Interface integration. We need a good way to present AI outputs to humans for review and to capture their input back to the system. That's a UI, UX, and system integration problem. If it's clunky, it might frustrate the human or lead to errors, like human thought they approved one version but AI was using a different version. Deferring responsibility. Sometimes humans might over-rely on the AI's suggestion and just approve without thinking, automation bias, or conversely, always override if they don't trust it at all. Getting the right balance of trust is tricky. Training humans to effectively work with AI, like trust when it's right, catch when it's wrong, is a challenge in organizations, but overall, human in loop is advisable in many cases currently. Many real systems are hybrid. AI does first pass, human does final check. Like an AI might generate a news article draft, an editor then edits and publishes. That's faster than editor writing from scratch, but still keeps a person responsible for final content. It's also often mandated in some sectors, e.g. GDPR, data protection law. Has a provision that individuals have the right to a human review of decisions that significantly affect them, so you can't solely rely on algorithmic decisions in some cases without human option. So, the idea is to design the agent's workflow to seamlessly include a person at key points. For example, in a flowchart you might see agent proposes action, human approval, agent executes. If not, maybe agent asks human for guidance or stops. This pattern will likely persist, especially in enterprise and critical applications, at least until AI is nearly flawless, if ever. It is a stepping stone to gradually increasing autonomy as confidence in the AI improves. Let's bring it back to data science specifically and tie these patterns and frameworks into how they can supercharge data workflows. We touched on some of this earlier in the lecture notes, but it's worth summarizing with concrete imagery. ETL automation. Think of the tedious pipelines we often build to move and clean data. Agentic AI can make those pipelines smarter and more autonomous. Using an orchestrator worker pattern, an orchestrator agent monitors the pipeline. It could automatically detect if a data source changed format and then instruct a transformation agent to adjust, instead of failing and waiting for a human developer to fix code. We can have an agent that, upon detecting anomalies or missing data, triggers a sequence to handle it, maybe using generative AI to fill missing values contextually. The ODSC example we referenced basically described dividing ETL tasks among specialized agents and managing via an agent orchestrator. They even allowed for dynamic adjustments, like not a static DAG, but agents deciding new branches if needed. That's quite powerful, a pipeline that could, say, decide mid-run. The data quality is poor, so I'm going to run an extra cleaning step or ask a human for clarification. Traditional tools don't do that themselves. Automated analysis. Agents can take on tasks like exploring data and generating reports. For example, a single agent might be prompted, analyze this dataset and give key findings. It will do some reasoning, maybe it has internal tools to run stats. Or multi-agent. One agent generates hypotheses, another agent tests them using maybe a Python tool and data, then they collaborate to produce a summary. We basically can mimic a data analyst's thought process with agents. Some might dig into data via Python tool calling, others might document findings, etc. Orchestration tools integration. Even if you use something like Apache Airflow to schedule tasks, an agent could monitor and orchestrate within that environment. For example, an agent ops concept is to have an agent learn from pipeline runs. If a particular task fails frequently, the agent might automatically add a check or alert or reroute data. Or consider scheduling. An agent might decide not to run a pipeline now because it predicts based on data changes that it's better to wait an hour. This is a more future concept, but plausible. Case AI ETL orchestration LangGraph. The ODSC article described using a library called LangGraph, like LangChain, but focusing on multi-agent graphs. They had a manager orchestrator, the node connecting others, and nodes as specialized agents for each step. Data retrieval agent, transform agent, loading agent, analysis agent. Because of this setup, if something went wrong at transform, the transform agent could maybe request help or flag it to Orchestrator, which could then adjust the flow, maybe skip load if transform fails, or try a different approach. If the data turned out to have an interesting anomaly, maybe the analysis agent could trigger an additional data fetch for deeper dive, i.e. the agents can add nodes to the graph on the fly, making it not static. This is very different from a fixed Airflow DAG that will just fail on error. It's an example of an adaptive workflow. Case, multi-agent analytics assistant. Let's imagine a scenario. A business user asks, "Why did our sales drop in region X last month?" The orchestrator agent interprets this question and breaks it down. It might ask a data retrieval agent to get sales data and marketing data for region X, and ask a data science agent to run some analysis, maybe correlation or anomaly detection. These tasks run, maybe in parallel. The retrieval agent queries the DB via a SQL tool and the marketing API. The DS agent runs maybe a regression or just calculates some stats. The orchestrator gets the data and intermediate findings. Perhaps it then calls an evaluator agent, which could just be itself doing a consistency check. Does the drop correlate with marketing spend drop or a supply issue in the data? Suppose it finds that yes, product stockouts happened that month. The orchestrator or a final report agent then compiles the answer. Sales dropped primarily due to supply chain issues causing stockouts in region X, as marketing spend and customer traffic were normal. And maybe a human manager gets that report with references to the data used. This story used Orchestrator Worker to split data retrieval and analysis, parallelization, data from two sources at once, evaluation, checking correlation versus just presenting raw data, and human in loop might be at the end to approve sending that to broad audience. So, in data science, Agentic AI can help at multiple levels. Micro, within a single analysis, double-checking a result. Mid, automating multi-step analyses. Macro, keeping pipelines robust and flexible. Real companies are starting to use this. One example, not deeply covered in our sources, is using GPT-based agents to monitor data quality, an agent that periodically reads some data samples and describes issues in plain language, which might catch things rules don't. Or using agents to automate feature engineering. Have an agent propose new features from raw data, like transforming or combining fields, and another agent validate if they improve model. We should also mention that not every data task needs multiple agents. Sometimes a single powerful LLM with tools is enough. But as complexity grows, data sources, steps, stakeholders, multi-agent structures, and the patterns we discussed become very useful to manage that complexity. Although we covered risks in detail in the notes, let's recap the key concerns when deploying these agentic systems and what we should do about them. Autonomy risks. By giving agents autonomy, you risk them doing something you didn't explicitly foresee. An agent might overstep, like ordering an expensive resource because it thought it needed it, or just make a wrong decision in a corner case. We saw examples of digital insiders risk from McKinsey. An agent can essentially act within systems with certain privileges. The mitigation is to have guardrails, constraints on actions, maybe an agent cannot spend above X dollars without approval, timeouts if an agent loops too long, kill it, and perhaps requiring human confirmation for critical actions, as we said with human in loop. Essentially, design the autonomy with limits. Communication failures en masse. With multiple agents, you can get issues like they might develop a cycle, agent A waiting on B and B waiting on A deadlock, or they might give inconsistent info to each other. If one agent's output is flawed, another agent might base its actions on that flawed info, error propagation. So when designing protocols, we might include timeouts if deadlock break out, or an orchestrator to break ties, or simply ensure clarity in message formats to reduce misunderstanding. It's similar to designing distributed systems. You need to handle partial failures and ensure convergence, like maybe limit the number of back and forth messages in a negotiation to avoid infinite loops. Also, if agents have different goals, maybe one is optimizing speed, another quality, you must align them or mediate conflicts possibly with an overseer agent or policy. Data security and privacy. Agents with access to data could inadvertently leak it. For example, if an agent uses a search tool, it might inadvertently send sensitive query content to an external API or include confidential data in a conversation with another agent that gets logged. If using an LLM API, feeding private data into it might be an issue if not handled properly. So you implement permissioning. For each tool an agent has, restrict what data it can send. Maybe before an agent calls an external API tool, have a function that strips or masks PII from the query. Use sandboxing. Run tools in a sandbox environment so an agent doesn't have direct OS access beyond what you allow. Also possibly have an agent or filter that scrubs outputs for sensitive info if they're going to be public. Example, ensure that the agent that writes summary for an external audience doesn't accidentally include an internal server path or code because it was in the data it saw. Logging is tricky. We want logs for audit, but those logs become another source of sensitive info, so they must be secured. Evaluation and testing. Standard software testing is already hard. Testing a system that can have non-deterministic AI behaviors is even harder. Multi-agent interactions combinatorially explode possible states. So how do we trust it? We need robust scenario testing, like simulate a variety of possible inputs, including edge cases. Possibly use an automated set of test cases where we know expected outcomes and see if agents do the right thing. You might also simulate misbehavior, e.g., feed an agent malicious input to see if it does something it shouldn't. Logging and monitoring comes in. Log every decision and communication an agent makes. This helps in debugging when something goes wrong, and in checking after deployment that things are running as expected. We could also have a monitoring agent, basically an evaluator running in parallel that inspects communications for anomalies, like if two agents get stuck in a loop repeating messages, the monitor agent could step in or alert. Version control of agent prompts and configurations is also important. If you update an agent's prompt, treat that like code, test it in staging environment to ensure the whole system still works cohesively. Governance policies. On the organizational side, define clear rules for AI agent usage. Identify decisions that must have a human in the loop versus which can be fully automated. Perhaps small cost reimbursements can be auto-approved by an agent, but large ones need manager approval. Ensure compliance with regulations. For example, EU's AI Act might classify an AI system as high risk if it does HR or finance decisions. Then you legally need certain logging, transparency, and human override capabilities. We must design those in, like the system should be able to explain why the agent made a decision, which is challenging, but maybe logs and agent reasoning traces help. Also consider ethics and fairness. If multiple agents are, say, scoring job candidates, we need to audit that process for bias. So governance might require periodic audits of agent decisions by an internal team. Outline what happens if an agent malfunctions. Is there an immediate shutdown procedure or fallback to manual process? Like if your multi-agent data pipeline goes haywire, do you have a way to turn it off quickly and revert to a simpler backup pipeline? That's continuity planning. Continuous monitoring. Once in production, treat it like a living system. Possibly employ an agent watchdog. For instance, some companies use a secondary model to evaluate outputs for tone or correctness before they go out. That's like running a mini evaluator pattern live. If it flags something like, this answer seems to have low confidence or possibly incorrect info, it could route to a human or trigger an alert. We can also track metrics, e.g., how often are humans having to intervene? If it goes up, maybe the agent model drifted, or a new type of query is confusing it. Or track outcome metrics. If agent decisions lead to some KPI changes, maybe agent approving refunds, track if refund volume is spiking unexpectedly. If an agent interacts with external world, have fail-safes, e.g. if an agent tries to call an API too many times, throttle it. Or simple, if an agent without human check tries to spend money like auto-order supplies, put a daily cap and alert a human if it's hitting that. The overarching message, multi-agent systems introduce not just technical complexity, but also governance complexity. They blur lines of responsibility a bit. If AI did X, who is accountable? Good governance says, always have a human ultimately responsible. This ties into requiring approval for critical stuff and maintaining audit trails so you can explain after the fact, this outcome happened due to these steps the agents took based on these inputs. So, to safely harness agentic AI, we have to implement these risk mitigations from the start. The technology is powerful, but without checks, it could magnify errors or cause compliance issues. And we want to avoid headlines about an AI agent that went rogue for our projects. To wrap up, generative AI gave us the ability to produce content on demand, but agentic AI goes a step further, allowing AI systems to not just inform us, but to act on our behalf in pursuit of goals. We've explored how that works conceptually and in practice. Remember the big distinctions. Generative AI is about generating outputs. Agentic AI is about taking initiative and using tools to affect the environment. In building agent systems, we lean on frameworks to simplify things, so you're not writing socket communication or manual prompt management from scratch. Tools like LangChain or AutoGen are your friends in implementing these patterns in code. We covered design patterns like Orchestrator worker, router, evaluator loops, etc. These give you templates to design your agent solutions. If you have a complex pipeline, consider the Orchestrator pattern. If you have multi-step tasks requiring iteration, consider Evaluator Optimiser so the agent can refine solutions. Use these patterns as building blocks. And never forget the safety and governance aspects. It's exciting to give AI agents autonomy, but we have to do so responsibly. That means building in human checkpoints, thoroughly testing agents under various scenarios, monitoring them in production, and having clear rules for what agents can and cannot do. If you implement an agent system in, say, a financial context, make sure it's impossible for it to, for example, initiate a huge transfer without a human involved. These constraints protect both the users and the organization. Looking forward, the trend is towards more such agentic systems. We might soon routinely have AI colleagues, maybe an AI data analyst that continuously monitors and answers questions about the company's data, coordinating with other AI services. Or multiple AI agents cooperating across departments, like one listens on social media for issues, another adjusts operations schedules accordingly, all with minimal human coordination. There are challenges to solve, like making agents more trustworthy, improving their reasoning to avoid mistakes, ensuring they align with human values, but research is actively addressing these. For example, better theory of mind for agents to predict each other, more transparent chain of thought to debug decisions, and robust fail-safe designs. Now I'd love to hear your questions or thoughts. Perhaps you're wondering how to apply a specific pattern to a problem you have, or what frameworks might fit a particular use case. Feel free to ask about anything, from technical specifics to broader strategy or ethical considerations. Thank you.